Hello everyone. For today's video lecture, we're going to be talking about steady flow devices. Alright, so steady flow devices. A steady flow device is any device that has a constant flow of material moving through it. So there's numerous applications of steady flow devices in engineering, including things like pipes, nozzles, diffusers, pumps. Anything that's really going to have a fluid moving through it is going to be a steady flow device for the most part. Alright, so if the device alters the momentum of the fluid, which happens in many cases, this is going to be either by altering the speed or the direction of the fluid flow. We're altering momentum, we need to have an impulse to make that happen. So a clear example of this in action is a fire hose. So when we have a fire hose, the nozzle on the end of the fire hose is going to work to increase the speed of the fluid. It's going to change the momentum of the fluid. And because of that, we need to have a fairly significant amount of force to hold that fire hose in place. So if we don't have that force, the fire hose is going to be kind of pushed backwards. The nozzles are going to be pushed backwards because of the fluid flow. All right, so in order to determine the forces at play in this steady flow device, we need to first examine the conservation of mass. So this is going to be important to deal with before we get to our impulse momentum equation. So steady flow devices, by definition, have a steady flow of material moving through them. That's where the name comes from. And the rate at which mass is entering the device will be the same at the rate at which is leaving the device. So mass flow rate in is equal to mass flow rate out, where that mass flow rate is going to be the amount of mass that comes in or out divided by the unit time. So it might be like, so many kilograms per second of a material moving in or out. And steady flow devices, if they're rigid devices, they can't kind of balloon up or get smaller over time. They're going to have a matching input and output here. All right, so that's our mass flow rate. And we're not always directly going to be given the mass flow rate, so we sometimes need to figure that out. So the fluid flow, the mass flow rate is going to be equal to the density of the fluid times the volumetric flow rate. So if we're given something like gallons per minute for a pump, we just need to multiply by the density to get the mass flow rate. And furthermore, if we have a fluid flowing through an opening with a known area, so like we can measure the diameter of the nozzle output, the volumetric flow rate is going to be equal to the average velocity times the cross-sectional area. Multiply that by density and we get our mass flow rate again. So all this comes together. We've got different ways of figuring out mass flow rate based on the information given. So density times volumetric flow rate, or density times average velocity times cross-sectional area of the opening. So whatever you have in your problem, you're going to need to kind of figure out your mass flow rates first. And do remember, density can change with temperature and pressure. Liquids are generally pretty stable. Density is not going to change a lot in these devices, but gases can change significantly. We can have a huge difference between the density at the input and the density at the output. So be careful with gases in particular. All right, so momentum, getting back to our impulse momentum equation. Generally, momentum was defined as mass times velocity. With a steady flow system, we don't use mass, we use mass flow rate. So we want to know the mass flow rate in, mass flow rate out, they're the same number here. And remember, mass over time is our mass flow rate. All right, so if we go to our impulse momentum equation, that was the impulse is equal to the final momentum minus the initial momentum. All right, so what if we just need to divide each term by t? So if we take everything, divide it by t, we'd wind up with the following. So I've taken my impulse and written it out as force times time. I'm assuming it's a constant impulse here, or constant force. So force times time over time, mass over time times final velocity, minus mass over time times initial velocity. All right, so simplify this whole thing. So on the left, the times cancel out, and then mass over time I'm going to write as our mass flow rate. So I wind up with the following equation. So the force is going to be equal to the mass flow rate, which is going to be the same input and output, times the change in velocity. So V final minus V initial. And these are vector quantities, so it can be a change in magnitude or direction for those velocities. All right, so that force in that equation, that's the force I need to exert on the fluid to cause that change in momentum. This is the force on the fluid itself. All right, so with this, it's important to remember that this is direction. So if we change the direction of the fluid, so we've got a kind of bend in a pipe, a 90-degree angle right here. Velocity or speed going in is the same as the speed going out, but I have a change in direction. So I would still have a force here because of this bend in the pipe. And when we have this, we need to basically break down our equation down into components. So the force in the x direction would be mass flow rate times the change in velocity in the x direction. Force in the y direction would be the mass flow rate times change in velocity in the y direction here. All right, so it's also important to remember the final conservation of momentum equation gives us the force the device would need to exert on the fluid in order to change its momentum. So with our pipe here, if we solved the equation as it was written, this is what we get. We get a force that was kind of going down and to the right, and that is the force of the pipe on the water. If we are worried about the opposite thing, it's going to be simply equal and opposite. So if I'm worried about what is the force the water exerts on the pipe, it's going to be equal and opposite. The water is going to be pushing the pipe up and to the left as it goes through this turn right here. So we're going to have a force that's equal and opposite. All right, so with that, that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.